Hello everyone. This is section 1.5, 5 key equations for motion with a constant acceleration. This is the most important section that deals with how to solve physics problems in kinematics. After learning a lot about graphs in the previous lesson, we should be able to interpret this graph. So the type of motion on this graph is represented by a non-horizontal straight line. So that means the straight line means that it's a slope that is a constant. So acceleration is constant. And since that is non-horizontal, that means it is not zero. So it is a non-uniform motion with a constant acceleration. We call it uniformly accelerated motion. Since that is a velocity time graph, we should be able to calculate area under the line. And area under the line is equal to area of the triangle plus area of the rectangle. Area of the triangle is base times height divided by 2. Area of the rectangle is length times width. Then we see for a triangle, base is interval of time. So for base is interval of time, and for a height is a difference between V final minus V initial. For a rectangle, length is interval of time and width is V initial. So after the next one is this is equal to half of the delta t V final minus half of the delta t V initial. And now plus delta t V initial. Now delta t V initial minus half of the delta t V initial is just half. So what is left there is half of the delta t V final plus half of the delta t V initial. After we factor half and delta t, we have V final plus V initial divided by 2 times delta t, which is equation number 1 in a kinematics. So we can say the displacement of the object that undergoes uniformly accelerated motion. So accelerated motion with a uniform or with a constant acceleration is average velocity times time. Why do we say average? Because this V final plus V initial divided by 2 is V average. So if we want to solve for V average, that is equal to a delta D over delta T. So those three equations in red are often used when acceleration is not known. So if we know V final, we know V initial, we know time, but we do not know acceleration, we still can calculate displacement. Now we know this equation. Average acceleration is equal V final minus V initial over delta t, or change in velocity divided by interval of time. So this is one of the most important equations in kinematics. As a matter of fact, there are just two equations, and this is equation number 2. But if we solve for final velocity, we get V final is equal V initial plus A average delta t. Now, we can substitute the final velocity in first equation. So let's say that we do not know final velocity, but we know V initial, we know acceleration, and we know time. So on this, we can replace final velocity on this equation here with what final velocity is equal is V initial plus AV delta t. So that's what we did here. Instead of V final here, we replaced with a V initial plus A delta T. Now we have V initial plus V initial, 2V initial, times delta T divided by 2, plus AV delta T times delta T is delta T squared, and that divided by 2. So 2 and 2 cancel. So what is left there is a V initial delta T plus half of the AV delta T squared. This is equation number 3. Same way, we can rearrange that equation and solve for time if time is missing. So we can have time is equal V final minus V initial over A average. And then we can substitute this in that equation number 1 that we have V final plus V initial divided by 2 times time, and time is V final minus V initial over A average. So now we have V final plus V initial times V final minus V initial. That means A plus B times A minus B, which is equal to A squared minus B squared. So this is V final square minus V initial square over 2A average. So that is equation number 4. And if we want to solve for different component of this equation number 4, we can solve for V final square, for example. That is equal V initial square plus 2A average times delta D, or V initial square is equal V final square minus 2A average times delta D. Now, the last arrangement that we can do is what if the initial velocity is unknown? Then we can do the same thing. We can rearrange that equation so we can solve for V initial. And V initial is V final minus A average delta T, and we rearrange this and we substitute V initial that is on equation number 1 with what V initial is. It's a V final minus A average delta T. So we can reach to this point as a V final plus what is V initial is V final minus A V delta T times delta T divided by 2, and then we can break those components. So V final plus V final is 2V final times delta T is 2V final delta T divided by 2 minus A average delta T times delta T is delta T squared divided by 2. So now 2 and 2 cancel. So what is left there is a V final delta T minus half of A average delta T squared. So that will be equation number 5. So delta D is equal V final delta T minus half of A average delta T squared. So we have now 5 key equations that you can use to solve kinematics equation in physics. So equation number 1, we can rearrange that equation number 1 to solve for different component of this. For example, if we want to solve for T, we have delta T is equal to delta D over V final plus V initial. And if we want to replace this average V final plus V initial divided by 2, which makes average velocity, you're going to have delta D is equal V average delta T. And from here, if you want to solve for delta T, you have delta D over V average. Or if you want to solve for V average, you have delta D over delta T. This is important Now, equation number 2. Equation number 2 is about final and initial velocity. So this is acceleration equation. So if we solve for v final, you'll get that one, which is called equation number 2. If you solve for v initial, you get this equation. And if you solve for time, you're going to get v final minus v initial over a average. So those combination of equation number 2, you might be very useful for you to solve a different physics problems when unknown might be different. Equation number 3 is delta D is equal to V initial delta T plus half of the A average delta T square. To solve for time, especially for projectile motion that we're going to learn in chapter 2, is you can use quadratic equation. So minus b plus minus b square, square root of b squared minus 4ac divided by 2a. So that is the equation to solve for time in a projectile motion. And equation number 4, you can actually solve for different component on equation number 4. You can solve for a average, which now they switch places with a delta D. And then you can solve for V final square is equal to V initial square plus 2A delta D, or for V initial, which is V final square minus 2A delta D. The last one is equation number 5. Again, you can have the equation number 5. You still can use that equation number 5 to solve for time using quadratic equation if you know final velocity. And those are pretty much all 5 key equations. And you can, with rearranging those equations, you can even have more equations ready for you to solve physics problems. Here are 5 key equations of the motion, uniformly accelerated motion. As a matter of fact, you have equation number 1 and equation number 2 for kinematics, because equation 3, equation 4, and equation 5 are just a combination of those first 2. Anyway, if you have those many equations, how can you decide which one you can use to solve a physics problem? It is right there. When you have variables in equations, and if you don't have acceleration, for example, you can use equation number 1. If you have A average, delta T, V final or V initial, then, and you don't have delta D, then equation number 2 is the one to use to solve the problem. So when V final is unknown, then equation number 3 is the one that you can use. When a time is unknown, then equation 4 is the one that you can use to solve for V final or a combination of any of those. And finally, if the V initial is unknown, then you can use equation number 5 to solve for any of those variables that are missing. Let's do some practice to solve a physics problem using those equations that we already just learned. So example, using uniformly accelerated motion equations of kinematics. A park ranger driving at 11.4 meters per second in a forest area suddenly sees a deer frozen in headlights. He applies the brakes and slows down at a rate of 3.8 meters per second square. If the deer is 20 meters from the ranger's car when he brakes, how close does the rangers come to hitting the deer. So the idea is that after he sees the deer, he hit the brakes, so that means that car will slow down, car will deaccelerate. The acceleration is negative. So acceleration is the opposite direction of the initial velocity. So let's write what is given, what is required. Initial velocity is forward. So let's do forward as a positive. So plus 11.4 meter per second. Average acceleration, obviously, slows down means a negative, the opposite direction of the moving forward. So it's a minus 3.8 meter per second square. V final has to be 0, although it's not mentioned anywhere there. So the car has to come to complete stop before hitting the deer. And displacement, so that means that what is that distance of braking distance? We can use one of the equations because the time is not mentioned here. That means the V initial is given, V final is given, and acceleration. So we can use equation number 4. That is delta D is equal to V final square minus V initial square divided by 2A. Then we know that all our given data are standard with a standard unit. So we are ready to plug those numbers in an equation and solve it, and that's 17.1. So that means it's 17.1, and the deer was 20 meter far. So 20 minus 17.1, he stopped 2.9 meter ahead of deer, so it's safe. Next, what is the stopping time? So time is not mentioned here anywhere. We can find it using what we have, the given data. So we can use that one of the equation that we derived by equation number 2. So if you go back to your notes and see the equation number 2 and solving for delta t, this is the equation that we can use. Delta t is equal to V final minus V initial over A. So V final is 0, V initial is 11.4 meter per second, and acceleration is minus 3.8 meter per second square, and answer would be 3 seconds. Here is another example of using those key equations solving uniformly accelerated motion. An astronaut is piloting her spacecraft toward the International Space Station. To stop the spacecraft, she fires a retro rocket, which caused the spacecraft to slow down from 20 meters per second east to 0 in 12 seconds. What is acceleration of the spacecraft? So what is given? V initial is 20 meters per second east. V final is 0. It will come to complete stop. Time is 12 seconds. Acceleration is required. So that means we should use a formula that involves V initial, V final, time, and acceleration, which is equation number 2, or equation of acceleration. It's very well known. So we can solve for acceleration. Take a look of the data. All of them have a standard unit, which is good to go. So acceleration is 0 minus 20 meters per second east divided by 12 seconds. And then acceleration is minus 1.67 meters per second square east. Remember what we said many times. Never leave an answer with a negative and the direction. So what you can do? You can flip the direction. That will change the negative to positive. So by changing east to west, we'll make that negative to positive. B. What is displacement of the spacecraft when it comes to rest. So, which equations should we use to calculate displacement? There are 4 of them. 3 of them involve acceleration, which we already just calculated. However, what if we made a mistake using acceleration at A? That mistake will carry over to B. So basically, we mess up B as well, and we do not get the correct result. So there is an option here that we can use this one formula that does not include acceleration, but includes V initial, V final, and time, which is equation number 1. So yes, we can do. Everything is a constant, everything is a standard unit. Then we can plug it in that formula, 0 plus 20 meters per second divided by 2 times 12. That will make 120 meters east. So by looking at those problems, you need to figure out which formula can include what is given, what is required at the same formula. But you have to have one unknown. So you can solve any problem by having those advices in your mind. So that's about it about this 5 key equations of motions. You need to practice a lot because which equation should we use comes very, very often. The answer for this one is practice, practice, practice. Thank you. I hope you enjoy it, and see you in the next lesson.